Okay, today we're going to look at the weight relief raise. We can see here a person in a wheelchair. They use this to decrease pressure on their buttocks so they don't get a sore. We can see that the starting position is the person in a wheelchair. They place their hands on the wheelchair and then raise themselves up using their triceps and shoulder muscles. So what we're going to look at today is we're going to analyze the use of their shoulder muscles in this activity. So what we're basically doing is taking a look at this biomechanical picture here, where we can see here's the spine with the shoulder girdle with the scapula and the humerus. We have two key muscles we're going to focus in on: the lower trapezius, which attaches to the spine of the scapula, and then to the lower six thoracic vertebrae, and then the latissimus dorsi muscle, which attaches to the humerus, and then to the spine and also the pelvis. So we can conceptualize this with a free body diagram to begin with. So we can start here with the spine, the pelvis, and then we can put the weight on there. So put the weight somewhere in the mid-thoracic region. And this will be the weight of the trunk. Put an arrow acting downward and a W. We can put over here that the weight of the trunk and head will make this equal to 500 pounds for this problem, or 500 newtons I should say. And then we could draw the muscle forces that are acting. And we know here, we'll draw the lat here on this side, so the force in the lat, not the trapezius. So the force in the lat on this side, and the force in the lat on the opposite side. We have the force in the trap, the lower trap, acting bilaterally, right? So here we have the force in the lower trap on both sides and the force in the lat. But we really only have to consider one side because they're both going to be mirror images if we assume it's symmetrical, which makes it a lot easier. So let's do that. So basically, let's get rid of the one-sided forces here, and then let's make the body weight half, because their weight would actually only have to be half. So we'll just say we're going to use half body weight. That equals 250 newtons. Okay, so we have almost what we need, but we also need the line of actions here. So the trap we made acting at 30 degrees, and we'll make the lat acting at 45 degrees. So we have what we need now to kind of solve the problem in terms of, can it lift? How much force do we need for these muscles need to develop to actually lift the trunk off the chair so that there's some weight relief? So we can put a coordinate system here, and this will be our vertical direction, and then this will be our horizontal. We really only need the vertical. Alright, so let's write out the equation. So we have the sum of the forces in the vertical equals 0. Okay, and they have to overcome body weight in order to lift the buttock. So since it's only half of body weight, and we know that body weight's acting downward, we can start the equation here by putting 1/2 W, and then we know FLT and FL both act up, so they're going to be positive. So plus FLT cosine 30 plus F lat cosine 45, and that equals 0. Now we have two muscles to solve for, so we need another kind of relationship to get this. So we can say that because of the PCSA of the lat versus the lower trap, we know that the FL is 2 times that of the F lower trap. So essentially, we've got our equation then that we need, and you can see we can substitute that in here. So basically, we can rewrite this as FTW plus FLT cosine 30 plus, and we can substitute this in for FL. So we know that 2 FLT cosine 45 equals 0. So now we can solve for this, and we have to kind of rearrange this so we can write here FLT. So the first thing we'll do is we'll subtract the weight from both sides, and then it'll move to the right. So we'll erase that here. Okay, and so we'll write that over here. So we'll say equals weight, half weight. Okay, and then basically we have this to deal with. So we can factor out the FLT, so we can put the FLT here, and then put cosine 30 plus 2 cosine 45, and then there's our kind of equation, right? So now we can solve for FLT. So we know that FLT, the lower trap, the force in the lower trap will equal 1/2 weight divided by cosine 30 plus 2 cosine 45, and this all equals 250 over 2.28, and then that gives us an FLT of 109.6 newtons. Okay, so then now we've got the lower trap force here, so now we just have to figure the lat. We know that the lat is equal to 2 times FLT, so we can just put in here F of L equals 2 times FLT equals 2 times 109.6. Oops, sorry. And that's going to equal 19.2 newtons. So for the weight relief raise for somebody that has a 500 Newton trunk, in order to move the trunk and get some space in their buttock, they'll need to produce 109 newtons of force in the lower trap and 219 newtons of force in the latissimus dorsi to raise and get some weight relief.